Here we go. So black box models such as neural networks are the only game in town in NLP at this point. For example, recurrent neural networks, this is just an example of these models. The method we're going to be presenting is not in any way specific to RNNs. It works on any incremental language model, but this is just an example. When you use an RNN, you take a sentence or a sentence prefix like the keys to the cabinet, and you get a representation, a hidden representation of each word in the sentence. And so our question is, how could you figure out, when you're looking at these hidden representations, you don't really know what the content of them is. When you look at them, they're just a bunch of numbers, vector space representations. And we want to know, how could you decode the information, in particular the syntactic information which is present in these things, and how could you, first of all, establish that that information is there? So in particular, we're going to be interested in cases like these three. We're going to be doing these sort of behavioral experiments like where you say the keys to the cabinet is or are. And what we're interested in there is for these representations for the words to the cabinet. So if you imagine that you are doing something like running an incremental parser over this sentence, your incremental parser is going to be maintaining representations of the syntactic state at each word. So for each of these black box representations, what we want to know is, can we adduce evidence that encoded in these numbers are structures like these? And we're going to be doing that through what we call a psycholinguistic method. It's a behavioral method of looking at how these trees are reflected in network behavior. So we're not just going to be saying, these are the trees, and we're going to find them. We're going to be asking on a deeper level, what is the actual information encoded in these trees? So these trees are not just annotations that make linguists feel happy. These trees encode in a human readable way absolutely crucial information about how the sentence can unfold in a grammatical way. And in particular, part of what's encoded in these trees is something like the fact that this kind of sentence, the keys to the cabinet is on the table, is not something that English speakers are going to enjoy finding in their text generation systems. And the keys to the cabinet are on the table is fine. So the key thing is that the fact that that word cabinet is inside that thing called a PP in the tree structure, what that encodes in part is that that is not relevant for predicting the agreement on the next word. So that's the behavioral consequence. That's the actual evidential basis on which we have deduced that these trees exist in the first place. So in terms of, if you have a language model, what that behavioral signal reduces to is going to be something like, you could look at the probability that the continuing word here is are given the final state versus the probability that it's is given the final state, and you'd better hope that the probability of are is greater than the probability of is. In order to get this right on a controlled set of sentences, you're going to have to represent something which is at least isomorphic to the information contained in these trees. So this is what we call the psycholinguistic method. And we call it the psycholinguistic method because we're essentially importing a methodology from the field of psycholinguistics, in particular the field of human sentence processing, which has been used for 40 years to deduce the data structures and mental representations that humans are using during language comprehension. So the idea is you design specially crafted sentences, specially crafted sets of sentences called items. You have something like the keys to the cabinet are a grammatical sentence. And in the case of the work we're going to be doing with language models, what you're going to measure is for each word, what is the surprisal of that word given the previous hidden state? The surprisal is just the negative log probability. This is the contribution to the language modeling loss. And we're going to be looking at models that are just trained on the language modeling loss. So you have the sentence, the keys to the cabinet are, and you can get the word by word time course of surprisal. And so in psycholinguistics, for 40 years, people have been doing this kind of thing where you look at special sentences and look at the reading times per word. And from the reading times per word, which are an index of difficulty, you can determine stuff like what data structures are people using, what are humans using during parsing. We're going to be applying the same method, but now we're looking at the time course of surprisal coming out of language models, adducing evidence for different syntactic representations. So you have the keys to the cabinet are. The key thing is you compare that now to some other sentence, a carefully controlled paired sentence like the keys to the cabinet is, the same except for one word. And what you're going to get is that the surprisal time course is the same up to that final word is, and then there's going to be a difference. And that difference is what we're interested in. That's the penalty for the surprising ungrammatical continuation. So we don't really care what the actual surprisal number is on any particular word. What we care about is these differences between grammatical and ungrammatical sentences, and that's actually the strength of evidence that the network is representing a particular syntactic structure, in this case, the prepositional phrase. And so we call this an error penalty. And so what we actually measure, our dependent measure that we're going to be looking at on our specially controlled sentences, are these differences in surprisals. Surprisal of is given the prefix minus surprisal of are given the prefix. So now I'm going to talk about what we've actually done, the constructions we've looked at, the models that we've looked at. So we looked at a set of 4 different neural network language models. The first that we looked at is what used to be the state-of-the-art LSTM language model from Yosefowitz 2016. This is trained on lots of data, and it's a large model in terms of the number of units it has. So these LSTM models have no explicit syntactic state representations. Our question is, have they developed them? Have they induced them based on their unsupervised training objective? We're also going to look at the neural network language model that was made public by Guler-Dava et al. 2018, which we saw in an earlier paper in this session. And we're going to look at these things called RNN grammars. So RNN grammars, these are models which actually do have syntactic structure embedded into the way that they compute probabilities of words. So these things are trained on syntactically annotated corpora. They have syntactic supervision. As a control for the RNN grammars, so RNN grammars have syntactic supervision, but they're also trained on much less data. They're trained on 2 orders of magnitude, pretty much less data than Guler-Dava. So we're going to also look at this other, we also just trained an LSTM on the same amount of data and the same data as the RNN grammar got. We call that tiny LSTM. So inasmuch as the RNN grammar does better on representing syntactic state than tiny LSTM, that tells you how much advantage do you get from the syntactic supervision. Good. So we're going to design special sets of sentences such that the neural network surprisals reveal evidence of syntactic state. And we're basically importing methods and analytical techniques. We're bringing over the whole apparatus of analysis from psycholinguistics, in particular from human sentence processing. We're going to study a number of kinds of syntactic states. So this is expanding beyond subject-verb agreement into a larger number of constructions. Our goal is to eventually basically reconstruct all the evidence for all syntax in terms of these behavioral tests. And so I'm only going to be presenting a subset of the constructions that we've looked at for time reasons. I'm presenting 2 of the ones that I find most interesting in the paper. There are many more. So we're asking 2 fundamental questions. Do the neural networks represent the syntactic state required for these constructions at all? And number 2, what particular cues do they use to say, aha, I need to start this particular state? Like, I need to start saying I'm in a prepositional phrase right now. How do they figure that out? What cues do they look at? Good. So now we're going to be looking at 2 phenomena, subordinate clauses and garden paths. So subordinate clauses are things that are exemplified by a sentence like this. As the doctor studied the textbook, comma, the nurse walked into the office. So note that this variant of the sentence would be very surprising and ungrammatical. As the doctor studied the textbook, period, silence, end of sentence. If someone said that, you would probably be confused. So this behavioral pattern is encoded in terms of a tree. In terms of something like this, you have an embedded sentence. The doctor studied the textbook. That's all part of this S prime thing, which is signaled. The cue for the onset of that thing is the complementizer as, and that means you have to have some following sentence. So basically, if you have a subordinate clause, this as sentence thing, you have to have a following clause. And that is one of the behavioral consequences of what it means to be a subordinate clause. There's a requirement of there being a second clause. There's another aspect, behavioral aspect of subordinate clauses, which is apparent when you compare these 2 sentences. So not only does the subordinate clause require a clause following, it also licenses one. So if I say the doctor studied the textbook, comma, the nurse walked into the office, it's a little weird. But now it's a lot better if I have as at the beginning, as the doctor studied the textbook, the nurse walked into the office. These are actually two dissociable effects. So we study this in terms of a set of 4 sentences. So we look at very many sentences with different lexical items. But they're controlled in this way, and you can consider them to be in these different conditions. And the relevant contrasts here, the differences in surprisal that are going to reveal evidence for subordinate clause representation, are this first one, which we call the no matrix penalty effect. That's the size of the surprisal hit you take when you require that second clause to happen and it's missing. And we measure that as the surprisal in the first condition minus the second condition minus the first. And we call that the, you get a size of a penalty there, we call that the no matrix penalty effect. The second effect, embodied by a subordinate clause, is that that second clause becomes more likely. In addition to taking a hit when it's missing, it should be more probable when it does appear. And you measure that by looking at the surprisal of that one, the final sentence, compared with the surprisal of the first sentence. So here are some results on these 2 dissociable behavioral signatures of the subordinate clause. So the first thing you could look at is the size of that matrix licensing, the no matrix penalty effect. How hard do you get hit with extra surprisal when you didn't get that thing that you required? And our Guler-Dava model has that effect. The old state-of-the-art LSTM actually does not show it at all. But they do, both of them do show in a huge way this matrix licensing effect. They both make the second clause more likely, but they don't always reflect the fact that it's required. Now expanding to our set of 4 models, you can see that when you add the syntactic supervision for the RNN grammar, now you get both effects in a huge and clear way. When you trade on the same small amount of data with no syntactic supervision in tiny LSTM, the effect sizes are all a lot smaller and you don't get the no matrix penalty effect at all. So in terms of reproducing the qualitative effect that is encoded by this tree, you basically need syntactic supervision or large data and a good architecture. So that's subordinate clauses. All neural network language models will show evidence for some aspects of subordinate clauses. Always licensing, not always requirement. And syntactic supervision is worth 100 times as much data for getting that qualitative effect. So the second thing I'm going to look at is garden path effects. We're going to go through this relatively quickly. Garden path effects, these are things like if you say, the woman brought the sandwich from the kitchen, and you imagine what your syntactic state representation is going to be like halfway through that, you probably think the sentence is done. Then you get a surprising word like tripped. So at first you think the sentence looks like that, but then you get the surprising word tripped and you have to revise it to this. And what that shows is that you had a preferred syntactic analysis for the previous words. So you can see that effect in a surprisal difference. If you compare this sentence, which gives you a garden path effect, to this one, which does not because it has these words who was, a syntactic cue that disambiguates and means you're never going to be confused. There's no local ambiguity. So in that case, we call that reduced and unreduced. We look at a surprisal difference. And there's a subtler manipulation where you can say the woman given the sandwich from the kitchen tripped on the carpet. In that case, the actual morphological form of the word given is going to tell you that this is a relative clause and not a main verb, and you should not get a garden path effect there. So comparing these two things, we can see, is the neural network using the morphological cue in order to figure out something about the syntactic state it should be in? And looking at the various models, our large LSTMs show a reduced garden path effect when you have the morphological cue. It doesn't go to 0, so they're only partially using that morphological information. Turning to the models with syntactic supervision, there's actually not a significant effect for the RNN grammar there, and the model trained on not a lot of data doesn't get it at all. So garden paths, all models represent this basic reduced relative clause thing, but they differ in how they infer the beginning of the state based on morphology. They treat morphology basically, they all use the syntactic cue, who was. They don't always use the morphological cue. They treat morphology as noisy evidence for a syntactic state. So wrapping up. So this is a summary of all the results. So for each construction here, I've broken each construction into basically an easy part and a hard part. So for example, for subordination, the easy part's getting the matrix licensing effect, the hard part's getting the no matrix penalty effect. And this is a different garden path, which I didn't talk about. You can see basically all the models get the easy parts of the syntactic representation. They don't always get the hard parts. In particular, basically it looks like you need the large data to get the hard parts. And syntactic supervision can also help, for example, in the subordination case. And bonus talk content, we also did it with Transformer XL. This is not in the talk. Transformer XL gets the easy part and the hard part of both the cases I presented. So overall, we have basic evidence, struggling using particular lexical cues to do these things. And neural networks do show, it seems they show a hard to predict pattern in terms of what syntactic states they represent and what they don't. But robust syntactic state representations are present as revealed by these behavioral tests across many various constructions. So something like this representation or a fuzzy version of it is there. All right, thanks all.
We have time for a quick question or two.
So let me start by saying I really like the work. I am gonna take issue with the rhetorical flourish with which you opened the talk. If you go out into the real world of people trying to solve real world problems, NLP, you will find that there is definitely a whole bunch of stuff out there that does not fit the description of black box models in NLP. That also includes a lot of the work that people are doing trying to focus on actual tasks and applications in the real world. So that, I preface by saying I love the work. It's just a little over the top at the beginning with that, but so I wanted to make that point. In terms of an actual question, I'm curious in terms of have you guys started to look at languages that have different word orders and also different morphological properties, because it seems to me that a lot of the effects that you're looking at here, as in psycholinguistics, are going to be very sensitive to that.
So we have done experiments on Japanese, and it was in a construction where the networks failed in both English and Japanese to capture the proper syntactic state. But that's a frontier on which we would like to expand.
All right, thanks. Any other questions? All right, let's thank the speaker again. Thank you.